Okay, Mal. Good day a todos. So good morning to all. So today, what we will do is to start talking about PLCs, so programmable computers for application in industry, in automation, and we'll study a bit of the components. This theoretical part is shorter and much more theoretical, so it's just a bit of general purpose information, nothing special. So the idea is that you have a process, which is here in the middle, and you want to get information concerning the process. That means that you want to capture or measure. I don't know. Let's see grandeza in English. Grandeza. Isso na cara. Eu não posso dizer grandeza, nem uma outra coisa. É, grandeza. Like meters. What is it? Okay. So you want to measure temperature, pressure, displacement, whatever you want. And you need to have some form of adding this information into your device, your computer. And let's call that an input translator. Then you want to have some command or control. So you want to do something with the information, and you want to do it in a way that responds to the information that you are measuring. Bom dia. Você é que é novo?
Eu sou o Bruno. Eu sou o novo aqui primeiro.
Terceira fase?
Engenharia de automação industrial, na estrada.
Ok. Você entrou na terceira fase?
Sim, isso.
Ok. Está bem. Já falamos um bocadinho. Vou só falar aqui da parte teórica e depois já começamos. Then, after you decide what to do, there will be some variables in your program that will be the outputs, and these outputs are translated into some actuation, some form of changing the procedure. For example, if this is a temperature control system, what you are measuring as an input is the temperature. Your command and control will say something like, my target temperature will be X, and my current temperature is Y. So let's compute some difference, and let's heat up the room. So the actuation would be to heat up, for example, to increase the temperature up to the target position, something like this, okay? So this is a loop, a continuous loop, where you read the inputs, you do some command and control, so some decisions based on your program, and then these decisions are carried out into some actuation. So what we do in automation to do this kind of things is always PLCs, not always, most of the time. So what are PLCs? PLC means programmable logic controller, and it's basically a computer. So it's a device which was projected to compute logical functions, the ones that we have been studying from Boolean algebra and primal maps. And these logical functions previously were executed by relays, okay? So mechanical relays or electromechanical relays. And the PLCs have replaced most of these relay-based controllers because they are much more useful or useful to use. It's easier to use them. So the idea is to take a logical decision. So to say when a given output will be activated based on some logical input. So typically a PLC has a CPU and a memory, which are very robust because they are used in industrial environments. So you can use them to control procedures, like I told you before. Typically, the choice falls upon a PLC rather than a computer, although now there are some industrial PCs, but the PLC has other characteristics which makes them very useful, and we will see this one now. So a PLC is based on a microprocessor, which has some instructions that the program that you download with, which are stored in memory, and then whenever you turn on the system, it just starts executing the program that you have downloaded. Okay, so you can do logic, like we've studied so far, but you can also do some other stuff like arithmetic, counting, timing, this kind of stuff. Okay, so there are some additions. It's not just pure logic. You have some additional tools in the PLC, in the current PLCs. So in terms of history, the idea, what happened was that in the 60s, there was a need to reduce the cost that were very large when you would change the control of an industrial system. So you had some power, some cell producing a vehicle or something like this. And then if you wanted to change the part for something else, you would have to change the logic of control. And to change the logic of control would be to change the whole electric board with the relays. You have to change them all in order to change to a different logic. And this would be very time consuming and costly. The PLCs came as a way to reduce the time and of course the cost. And they were very flexible because they can have a given logic and then they are reprogrammed, and we'll be able to, in the next second, have a totally different logic, okay? So this is like a way to program logic. That's why they are called programmable logic controllers, because they are programmable. You can change the logic. So the first PLCs were installed in the 60s, and soon they have been seen to be a great improvement. They were easy to install, to program, or to reprogram, and they would occupy much less space when compared to the electric boards. So in terms of why the PLCs were successful, it's because they were very safe, and they had electric circuits that were protected, and they were able to perform in the factory floor in a very robust and efficient way. So that's why they are also an option nowadays, because you don't expect the PLC to fail very often, at least not before working 24 hours a day for 10 years or so. Second factor had to do with the programming language. Initially, it was called Ladder, and this programming language was, that's the one we are using still in the Siemens, and it was very close to the language that was used by the electricians that would do these logic controls based on relays. So it was very easy with this language for the electricians, for the technicians, to go from what they did before, which was electric board with relays, to programming PLCs with this ladder language. If it was in Python or C++, they wouldn't manage. With this language, it makes it very easy. Actually, you've been programming already. I think you know, and you also have this feeling that it's very easy language to use. In the 70s, the microprocessors were introduced in PLC, and that improved the performance of the PLC, but this was not a big change. In any case, the PLCs have been growing and growing. Their application in the industry has been growing and growing. Now you can find PLCs just about anywhere where there is automation. Well, in automotive industry, mechanical industry, anyway, I don't have to enumerate because just about everywhere you go, you can find a PLC. Okay. So, in terms of history, as I've told you before, relays were used, electromechanical relays, in order to do the control logic that you would need. Of course, that you would need to combine several relays in order to do this control logic. And the PLCs would provide a good immunity to electrical noise, easy interaction with inputs and outputs. That's one of the big advantages of the PLCs when compared to a PC. So for me, the PLCs, the game changer from the PLCs to a PC, because you can always say, why don't I use a PC? Because when you do your program in the PC and you decide something, you still need to put that decision out. So you need to have some way of outputting your decision. And this is not so easy as in a PLC. In a PLC, you just activate Q01, and there is a relay that is activated in the output, and you immediately can activate some motor or anything you want. So there is a very easy interaction with inputs and outputs. There is a cyclic operation. So as I told you before, the PLC is running continuously the program in loop, and this loop is quite fast, and at most. So this is close to a real-time system, or in most of the times a real-time system. So that means it's good enough for the application, it's fast enough. So it works forever, the PLC. So as I told you, it has a very high longevity, it doesn't cost so much, and the programming is very useful. So this is an example of where you put the PLC in an industrial control system. So you have some computers up here, and then the PLCs are actually closer to the machine. Okay, so this is just actually the PLCs are here. So this is just to say that in a big industry, The PLCs are the computers that are very close to each machine. Typically one PLC per machine or more than one, but then they would communicate nowadays in the times of Industry 4.0 even more. They would communicate with the mesh, the enterprise system or databases, and but a PLC is usually devoted to a given machine or dedicated. So in terms of architecture, which are the components of a PLC? Typically, in the center, you have, of course, a CPU unit, because a PLC is a computer. Then, for you to store the program, you need some memory. Typically, the PLCs have two different kinds of memory. The first is the program memory, which is the retentive memory. What does it mean? It means that when you put there something, even if you shut down the system, if you take away the power, it will still remember. So that's like your hard drive, okay, in the computer. And that's where you store your program. Then it has a different kind of memory, which is a memory that is transient. It works, so you can store stuff there while the system is running. That would be the state of your variable I00, the state of your variable I01, and so on and so forth. But then if you shut down the PLC, it will not remember whether I00 was true or false. It starts again, and by default it will be false or something like this, okay? So one of the memories for the program continues to be remembered even if you shut it down, the other one does not. And this memory that is transient is similar to your RAM in your computer, okay? What else? Then, of course, you have some input circuits. So you have some circuits which allow you to easily, that's one of the big advantages, get information from the outside. These are electrical circuits. So typically all the sensors that we use will produce electrical signals that are read through the input circuits. Then you have the output circuits. It's the other way around. So once you decide something in your program to turn on a variable, it will have a physical electrical effect on an output circuit, which you can connect to some motor or some actuator. You have a power source, of course. And then for programming the PLC, in the old days, sometimes you would have a programming console. These programming consoles are still used for manipulators, for robotic manipulators. They still use some consoles. But for the PLCs, so, and then you would somehow talk to the console with your PC. Nowadays, for the PLCs, you don't have a programming console. You directly program it with the PC and the software. That's what we are doing, okay? And that's it in terms of the components. As I've told you, this theoretical part is very soft. There are some other slides which say more or less the same. I will go through them just again. This is the same. So consider that your program is executed cyclically. In each cycle, you need to know what happens first. So first, the inputs are read, then the logic, or that means your program, is executed, and finally the outputs are actuated if need be. Okay, I went through here. So this is another example. So you have the CPU and the memory in the center. On the left-hand side, you have the input module with some sensors. So you have here a switch and a push button, something like this. And then on the right-hand side, you have your output module. And you would be able to turn on a lamp or some motor, something like this, okay? Nothing special. This is more of the same, just for you to have some information, some additional information. And still here, it's more of the same. So the same idea, just to tell you that the main components are the input module, the central CPU, also with memory, and then the output module. Yeah, this is an example where I have some inputs, and then you have a pump, a centrifugal pump, and some conveyor, and or an electric motor, or a lamp. In terms of outputs, you can have whatever you want, provided they are actuated electrically. So now, how does your program run? It will run something like this. It is running cyclically, and then first you transfer your program's state to the outputs. So here it's starting first by activating the outputs. Then you read the inputs, and finally you process your program. Typically, this is a cycle, so you can start anywhere you want. Typically, I start in number 2. So I always say, read the inputs, process, turn on the outputs. Here they are starting with the outputs. I think it's more confusing this way, but it doesn't matter because it's a loop. There is actually another slide here which will show you. Okay, so this is just to show that you can also have PLC that operate in racks. Racks are ways to assemble more modules easily. For example, I need a module to communicate with Ethernet, or another module because I need more inputs. You just add it to the rack. They are expandable, basically. And these racks are like, by the way, these racks are like your PCI in your computer motherboard, not the laptops, the real computers. So you can buy a new graphics card and add it to the PCI expects something. And this is similar to a rack, okay? Sometimes you have a battery, some communication ports. If this is important, you can just read it later on. Okay, so again, you can measure physical properties like speed, temperature, pressure. And based on these measurements, you can do some activation. What's in the middle is the control that you write in your program. So the PLC, with the PLCs, you can directly connect to your sensors rather than having something in the middle. There is something in the middle, but it's incorporated in the PLC, which is the input module. And the output is the same. Typically, there is the electrical isolation, so typical optical isolators, which will make sure that even though you connect something that doesn't make sense to the inputs, it doesn't destroy your PLC, okay? So as I said before, they are very well protected. This is one of the protections they have. So if they work for the students for many years as they have, that means they are perfect. Okay, how about inputs and outputs? What do we have? So you have many. For example, you have some selection commutators, some push buttons, so some buttons that you can push or that you can rotate. You have photoelectrical sensors. These are what you see in your elevators. So when the door is closing and you go inside and you pass in front of that wind, the door starts opening. That's because it picked you up, it picked up an obstacle. So you have push. These ones I don't know how to say in English, but you can see here. This is an example. How do you say this in English? This one. It's a mechanical figure. It's like pressing a button with a mechanical movement. What else? Level sensor that will detect if there is water or not. We will use one of these for this week's practical assignment. Then you have many other things. I will not go through all of them. Then in terms of output, you have alarms, control relays, lamps, valves, motors, anything you want that you can basically plug in. Here, another example. I will not go into details. Nor here, this is not important. Yeah. This was hidden, but it doesn't hide here. Because I printed the PDF. So if you go and see, you won't see those slides. So in terms of programming devices, this is an old slide because, I mean, you can see from the look of it, it looks like an 80s computer, an 80s calculator. So we don't use this anymore. Most of the times we directly program from the computer, the PLC. And then, of course, we have many types of PLCs, from the micro to the mini to PLCs in racks. You can spend very little or very much depending on your needs. So when the PLC starts, when you turn on the power, it will do some initialization, and that's done only once. Then this is what I like. First, you read the inputs, then you solve the logic of control. That means you execute your program. Then you activate the outputs. Okay, that's it. And you can know that this runs in about 10 milliseconds tops. Sometimes more, sometimes never, sometimes less, never more. This is the same, just another way of showing you that 0 is initialization. So it will start with 0, and then it will do the loop 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay? Nothing special. And that's it in terms of PLC. So I'm going to stop here. Next week, I will talk about ladder programming. There is how to say, a lack of synchronism between the theoretical part and the practical part. So I will formally theoretically give ladder programming, even though we are already using it. But I don't have a way to synchronize things better, because the only way I would have is to spend the first 3.5 hours speaking about theory. And only then I would say, okay, let's touch the hardware. But I think that's less interesting for you. So, I mean, you will manage, I'm sure. Okay, so for this week's practical assignment, what do we have? So we have a watering system. Let me just download the PDF again. This is where my hidden slides appear. Okay. Okay, so we have a watering system. This is your assignment for this week and the next. Você não tem o Zoom aí? Está no Zoom.
Como que faço? Não sei.
Você já tem sempre o Learn?
Não sei.
Eu já não tenho o Play. Já não, podia ter dito, cara. Esteja à vontade para interromper. Então, so the idea here is that we use the actual PLC to test. So we are going to program first with the simulator. We always start with the simulator, but you shouldn't take until next week or still with the simulator. You should go faster. And so by the end of next week, we should see the program running in the PLC and in the HMI. And the idea is that we do a program for the PLC and a panel, actually more than one panel for the HMI. And we are going to use timers. Okay, so we are going to add a new functionality rather more than logic, which is the use of timers. You will see what. We are also going to talk about the graph set. Again, I'm going to speak about the graph set in a very basic way. Graph set is a way of organizing your program conceptually, which then you can take as a means to do your own program. But we will discuss this first. Then we can connect some buttons. If you are fast, you can try to connect some buttons and some lamps. Okay. So this is just generics. Let me go. This is for you to read something about the PLCs. And okay, so in terms of programs, we are going to be talking about the way that PLC programs should be structured. This is not mandatory. This is a convention. It's not my convention because I don't work with automation in the industry. But the other professor, Aula, that is going to be teaching from the middle of November onward, he works in an automation company, so he has lots of these conventions that are useful for you if you go into some company to work. It's useful. So you should be careful. As I told you before, you can use the memory, the internal memory, the AMS, for whatever you want. But sometimes to have all the freedom is not good. So they created some conventions in order for people to use special parts of the memory for different functionalities. And this is what they are talking. For example, if you want to do some variables for interchanging information with the HMI, you should be using the scope of the range of memory from M100 to M129. For example, if you have a PLC that operates several stations, station 1 should be from M10 to M19, station 2 should be from M20 to 29, something like this, okay? And then there are special memories that are always used. For example, if you are in manual mode, that should activate M2.2, automatic mode M2.3, and so on and so forth. You don't have to memorize this. You should just read it before you start doing your program, and then use these conventions. Okay. Okay. How do you call your variables? So in the examples we've done before, we would call the variables whatever we wanted. In this case, we also have some conventions, and the idea is that you give the electrical identification underscore some summary description. For example, SB1 is an electrical notation for a switch button. SB1 because it's the first switch button, and then underscore loop start or cycle start. Okay, so that would be a good naming for the variable SB1 cycle start, for the variable that starts the cycle, the automatic cycle. An example for an output. YV is the notation for an electric valve. So we would have an electric valve that would operate a cylinder, that would make it go forward. So we call it YV11 because that's number 11. Move forward horizontal cylinder, something like this. Okay. Some internal variable, for example, here. You say something like automatic open gate, something like this. Okay. So of course, if it's an internal variable, it doesn't have an electrical reference because there is no electrical connection in the electrical board. What else? You should also split your program into several functions, in several XT. In this way, so you should have an XT for managing the functioning modes. So the logic that will decide if you are operating in manual or in automatic mode should be in a single XT. And it should activate its outputs. So the logic is something like that. For example, suppose my machine is always automatic. So that would be a network that would activate. So automatic mode is this, M2.3. So that would be M2.3, okay? Sorry, M2.3. So always, because there's nothing in between the left and the right-hand side, always activate M2.3. In this way, I would be working always in automatic mode. So, for example, if I wanted to work in automatic mode only when I would have some button for automatic mode turned on, I will put here my button, switch button, 1, auto. And only when my button is activated, I have automatic mode. If I don't have my button activated, this is a negation. Sorry, again. This slash here means negated. So that means that the variable I put here, SB1 auto, must be off in order for the energy to flow to the right-hand side. And in this case, I would activate M2.2, which is the variable for manual mode. Okay. And this part here is a network with the control for the function modes should be in a special XC for the function modes. Okay. And the same for the what happens in the logic inside the manual mode, inside the automatic mode, how to activate the outputs, and so on and so forth. I will provide you with some examples of how the program should be organized. In terms of graph sets, so graph sets, as I've told you, are a way to design a graph which will explain the core of the functionality of your program. Typically, this is how the automatic mode works. So the graph set is only for the automatic part, which is often the most complex, and it describes a sequence of events. So when you are doing something in a machine, you have to do something, then wait for the effect to occur, then do something else. But there is a sequence of events, and this is what you store in a graph set. When you have a sequence of events, you have to store something like this. Okay, so for example, this would be the start. Then you would have the advance of your cylinder. Here is the condition of when you transition from this state to the next. So each square is a state. and then you will go to this state where you are doing some action number 2, which is turning on some lamp or so on and so forth. Okay, I will not spend a lot of time with the graph sets. I will explain them later on. So I'm just going to quickly talk about, perhaps later on, I will talk about them, not now. Now, for our problem for today, it's to design a watering system. Okay, so suppose that you have a PLC in your home and you have a big lawn with several stations for watering the lawn, and you shouldn't turn them all at once because that's going to be ineffective in terms of electrical. You will have a big peak, so you can just water that side and then water another side. We call them sectors here, and what we want then is to implement a watering system that somehow does what we saw in the previous figure. So we want to water this sector, then some other sector, okay? So we want to implement a sequence of watering different sectors. First sector 1, then sector 2, and so on and so forth. So we are going to consider 2 functioning modes. We are going to consider a manual mode and an automatic mode. So in the automatic mode, we start there. What we want is to do the following sequence. First, you are going to water sector 1 for 3 seconds. Second, or after this, you are going to water sector 2 for 6 seconds. Then sector 3 for 4 seconds, and then sector 4 for 8 seconds. Okay? Suppose that sector 1, for example, is smaller than sector 4, that's why you take less time to water. This is the automatic mode, what the system should be doing in sequence, in automatic sequence. The manual mode should be able to give you some button where you say, start watering sector 3, and you push the button, it's continuous watering, then you release the button, stop watering. Okay? This is for example, if you see some part of your lawn which is in entire need of being watered, you just go there and manually you do it. So, describing the functioning. So the watering sector should, the start of watering should occur when the previous sector finishes. That's the sequence that I've shown you here. So you start 2 after 1 finishes, you start 3 after 2 finishes. Then the water should be suspended. So you cannot be watering if you do not have enough water in the well, and you have a sensor for this. This is BQ3, which is a detector, a water level detector, which will detect if you have enough water in your well. So it's like, suppose your well is like this, and you put your sensor in the bottom of the well. So as long as it's giving a signal on, electrical signal of 24 volts, it means that water is there. As the water goes down the sensor, falls below the sensor, it will start saying there is no water. So that means you don't have the minimum amount of water to operate, so you shouldn't move on. So you need to have BQ3 true in order to proceed. In terms of inputs and outputs, they are listed here. Okay, so you have to you do have to abide to this definition. So the memory slots are already defined. The names are not defined, but you can extract them from the electrical reference and the description. And you should go to your PLC tags and create all these variables. Then you have to develop all these FC, okay? So some of them may be empty, but for now, let's create them all. So you have to create FC1, FC11, FC12, 15, and 18. So FC11, FC1, for example, is the functioning modes. I've told you before how they can how it can be designed when I draw the logic for when to be in automatic mode and when to be in manual mode. Actually, there is a button here, which is button S01, which likely will be the commutator for manual and automatic mode. So if it's false, it should be manual. If it's true, it should be automatic. Okay. So then you have some variables. what you should put in the variables table. For example, for SA1 that I was talking about, you should call it SA1 underscore select automatic mode or manual automatic, something like this. This is for naming your variables. And then in your PLC, in your HMI, you should have two screens. One screen that should be the home page, so the entry page that should say hello and whatever else you want, hello, watering, something like this. And then you should have a button for going into manual mode and another button into going into the auto mode page. This doesn't mean that you go into manual mode immediately. It just means that you go into the page where you can control in manual mode. And in this page, for example, for the manual mode page, I should be able to see, for example, here, I'm just saying you can change the layout if you want. Here, I should be able to see the output, so YV01 through YV04. These are the electrical signs for the electrical valves that will turn on the watering. So this is just a monitoring part, monitoring of the system. And here you should have some buttons for pressing and for turning on. For example, here is turn on YV01, something like that. So if I press here, what should happen is that YV01 should be activated. Okay. Again, this is some control logic that perhaps should be in manual mode or not. We'll get it. In automatic mode, what I would like to see is the monitoring. So let's put here something for the monitoring as well. It's the same monitoring that before. And we should be able to know where the system is. So we are going to design a graph set similar to this one. Okay, and we should put the graph set there. So we should put something like this over there. I will call it graph set, okay? And I think that's it in terms of, yeah, okay, so that's it. Now, I'm just going to design the graph set with you so that you know how to start, okay? So you should always start with the graph set and then you should start, only then you should start implementing your program. So let me try to design the graph set and perhaps the code as well. Let's see. So start a new. Okay, so now I think I can do something like this. Okay, so now you know how the system should work. And so we have to design a graph set for the automatic mode. So the graph set for the automatic mode should be something like this. If you take a look here, graph sets always start with an initial state. So a state is what how the name, like the name said, is a state where the system is. So currently, for example, if my system begins and it's just waiting to begin, it's in the initial condition state. So let's call it state. Well, by the way, I call states with the letter S from state. So I'm just going to say S0 is my initial state. Okay, so this is my initial state. This is where I am. Now, this is the state. In a rectangle on the right-hand side of the state, I can say what I must do in my initial state. So these will be my actions for a given state. In this case, I don't think we have any action, so let's just continue. Okay. Now, so suppose that you enter automatic mode and you're still not watering anything. What you need to do is to start watering the first sector. Okay. Now, if you take a look at the variables here, there is an SP02, which is the pressure button to start the automatic cycle. So we have to go from state S0 to state S1. S1 would be, let me just write the description here, watering sector 1. So I'm going to start watering sector 1 when I get SV02 pressed. And what I put here as a transition, so this in the middle is a transition from between state SV02. So how do you read this? You read it in the following way. You say, okay, I am going to go from state S0 to state S1 if I am in state S0, so I must be here, and this must be true. That means if my state is activated, my previous state is activated, and my transition condition is true. It's also called receptivity. Okay? So this is how you read it. And now, based on this, we can continue. So, for example, we can continue to state S2. Perhaps I can compress this, or else I will not have enough space. S2. State S2 will be watering sector 2. Okay, and now when should I stop watering sector 1 and start watering sector 2? If you take a look at this, where was it? Sorry. Here in the description, we should water sector 1 for 3 seconds. Okay. So the idea is that when you start watering sector 1, immediately you should start counting. You should click a timer and wait for 3 seconds. So we are going to call here start T on 1. Okay, so T on, it means timer on 1. And here we say timer on bigger than 3 seconds. Okay. So again, when you enter S1, that means when you start watering sector 1, you are going to click and to start counting sometime. So you start counting sometime, and then you are only going to jump from state 1 to state 2. That means you are only going to stop watering sector 1 and start watering sector 2 once the timer that you started is bigger than 3 seconds. So after 3 seconds, you switch. If you have any questions, let me know, okay? Then it's more of the same. It's all very similar. Oh, sorry. I'm always going to the other side. So again, I'm going to create here state S3, which will be watering sector 3. Okay. And it's the same in this case. So I need to be, if I want to transition between state 2 and state 3 after 6 seconds, it's here. That means I need to start a timer. When I enter state 2, I'm going to call it T on 2, because that's timer for sector 2. And I'm going to move from sector 2 to sector 3 once T on 2. Oh, by the way, I made a mistake here. T on 1 bigger than 3 seconds. And here, T on 2 bigger than, in this case, 6 seconds. Okay. It's the same for the following. Now I should wait for 4 seconds. So I'm going to start T on 3. I'm going to transition once T on 3 is bigger than 4 seconds. And I am going to go into state 4 in this condition. When I am in state 4, I should be watering in sector 4. And I should also start some timer on 4, which I will use to transition from state 4, so T on 4 bigger than 8 seconds in this case, 8 seconds. I will use to transition to back to where I was in the first place, okay? Okay, so try to understand what's happening here. I start from S0, my initial state. Once someone presses the button for starting the cycle, I will jump into state S1. Here I am. Oops, sorry. Here I am. Okay. Then I start watering, but I also start counting 3 seconds. Once these 3 seconds elapse, I'm going to transition to state 2. Now I'm watering state 2. And so on and so forth until I get to state 4. When I get there, I'm going to start counting until 8 seconds. Once 8 seconds are gone, I go back to state 0, and I'm going to wait for someone to press the automatic cycle again. Okay. Any questions? No? Now, what's missing here? What's missing are the outputs. So you can create here, well, not with red, let's first do it with, yeah, something like this. So you should create here a second square, which is where you're going to put some outputs. So let's see what kind of outputs we have. So if you go into these tables here, which are, when I'm going to search for them, here, these are the outputs that we have. Output. So we have, let's start with the easy ones. A valve to water zone 1. So once you, this is an output, Q01, that's the address of an output. So YD01 is the electrical reference for an electric valve, 01 because it's number 1. And that will be plugged into the watering system of zone 1, of sector 1. So when you are in state S1, you are going to be watering section 1. At that time, you should turn on YD01. So my output will be YD01. Okay? When you are in sector 2, it's the same for YD02. And the same for YD03. And last but not least, YD04. Okay? So we've covered all these 4 outputs. Now we still have this one. That's HL00. It means the lamp that should indicate that you are operating in automatic mode. Okay. So in all these states, we are in automatic mode. Even if we are stopped in state 0, we are in automatic mode. So we should activate HL00, the lamp, in all of these states. So we can do something like this. Okay. That means activate the lamp all the time in all states. Any questions? No? Okay, good. So in terms of PLC code, as I told you, you can have several stuff. You can have the FC1 function mode. This FC1 is quite easy. What you need is to activate outputs M 2.2 manual and M 2.3 auto. Okay, these are the variables that you need to activate. I don't know if you remember, but they are up there. I'm just going to check it because I never know. Yeah, these two. Okay. So when should I activate these two? In the case of our system, we have a selector. We have a button that will tell us whether it should be manual or automatic decision. Okay. So we are going to say something like this. So we are going to call the button SA01 underscore manual auto. So when this SA01 is off, it should be manual. Why do I know that off is manual, one is auto? Because it's here. Manual, there is a 0 there, automatic, there is a 1 there. Okay? Then SA01 underscore man auto. When it's on, it should turn on auto. That's it for FC1 functioning modes. Okay. Now let's go into some other. Let's go into some other. Let me see. I just wanted to go to the automatic mode last. So in manual mode, FC11, I don't think we need to do anything right now. I'm not sure, but I don't think we need to do anything. So manual mode. So, okay, I will not do it. I'm just going to do it in automatic mode. That's the hardest thing. Auto mode. So what do you do if you are in automatic mode? By the way, don't forget that you can only do this graph set if you are in automatic mode. So you need to check some initial conditions here. Then that means that you need to be in automatic mode. M2.3 must underscore auto must be true. Okay? Otherwise, you cannot do any of this. Actually, this M2.2 auto equals true is true. It should be there for all the state, but I only write it there. So in the automatic mode, what we have to do? We have to write a network, and this is the main goal of this class, is to tell you how you go from the graph set directly into the ladder program without just by using some recipe that is always the same. Okay. So as I told you, when you are in state 0, well, actually, state 0 is an exception, so let's start with state 1. So state 1 should be activated when? That means that you should write down a network. Can I somehow, just a moment, okay? Let me try to do something here. Okay, okay, now crop. Like this, like this. Okay. Now, I should go to my gallery. At the moment, I'm trying to organize this so it's easier. Okay, now my gallery, where's my gallery? Okay, here it is. Now I open my notes. And I split screen this with my gallery. Okay, now yes. Okay, so this is, oops. This is our graph set on the right-hand side, and here we are doing our network. By the way, this is going to be a bit longer, so let's change the page. Actually, I think I can put it continuous. Do you know what page setting? No. No. There was an option. No. Okay, again. Okay, so we need a new page. So if we need a new page, I'm just going to take this away into a new page. Okay, auto mode here. So, as I told you, we are first going to work on state S1 because S0 is an exception. So let's start with state S1. For state S1, we need to know when to activate it. So the output, the goal is to say when each state will be activated. That means we start with this. Right? So this is state 1. When is it activated? So it's going to be activated when we can see it from the graph there. State 1 is going to be activated when we are in state 0 and SP01 as SP02 is activated. Okay, it's true. So we are going to activate state 01 when we are in state 0. This is the previous state. And we are in SP02. Okay. So this is what I call this the activation branch. This is the activation branch, which is composed of a first part, which is the previous state, and the second part, which is composed of the transition condition. Transition conditions in plural because it can be more than one. Okay, and that's it. This is when you go into state 1. But remember, the PLC is operating in loop. So that means that if, sorry, this is state 2, no? State 0 here. Yeah, the previous is 0. Thanks. Remember, the PLC is operating in a loop. So if in a given loop, one is state 0, then you jump, because one is state 0 and you have FP02 true, you jump into state 1. Then in the following iteration, this network will not be true because state 0 is not true anymore. Okay. So that means that if you go from state 0 to state 1, this is your activation branch and it works for jumping the first time to state 1. Now you need a second branch, which I often call maintaining, sorry. Maintenance é mais reparação. Maintaining branch, okay? So this is when we should continue in state 1, okay? So when should we continue in state 1? We should continue in state 1 if we are in state 1 and if the transition for the next state is not true. So in this case, I forgot how we can do this. It's the on. Yeah, better. Yeah, so we can say when we are in state 1 and we are not in state S2. Right, it's better. Regardless of things. Okay. So we are going to continue to be in branch S1 if we are in branch S1 already, and we are not in branch, sorry. We are going to continue to be in state S1 if we are still in state S1. So this part here. This part here is the current state. And this part here is the next state. Okay. So that means that, so again, I'm going to continue to be in state S1 because of the maintaining branch. And that maintaining branch tests if I am in my current state and I am not in my next state. Okay, simple. Now, I'm going to create a bit more space for state S0. I think it's going to be needed. Okay. Now, we continue to state S2. So when So now for the state S2, we are going to be there. Hey, Eric, can you help me? Can you tell me what I should put here for the activation branch of state S2? S1, yeah. Yeah. In terms of ladder, it's like this, T on. Because T on will activate an output, so it's just something like this. So from the moment that you enter state S1, it will start feeding this timer, but it will have here a time of 3 seconds. And only after 3 seconds of the energy flowing to the left-hand side, it will start putting energy to the right-hand side. So that's it. Thank you. In terms of maintaining, it is going to be the same. So I will maintain S2 while I'm in S2, and I am not in S1. Okay, that's it. And this is quite simple for the other cases, because they are very similar.
Previously we said that when we implement the new branch, we have to be in the different state and not in the next state.
Yeah, I made a mistake again. Thanks. This should be F3. This is what you do? Thank you. So for the state S3, we are going to activate it when it's a play. What? Yeah, what? So ILC, what should I put here? So for the activation branch, West U, the key. So here I should put the previous state. The previous of F3 is F2. Right? S2. S2. Oh, sorry. Sorry. Made some mistake. So here goes S2, right? Thanks. And in the timer, which timer should I use?
T 6 seconds.
So I call it T on 2, right? I call it T on 2. T on 2. And here's 6 seconds, right? And that's it for the activation branch. How about the maintenance branch? Is 2. S2 is the current state here.
It's 3 and 3.
Look here. This is the current state. The current state in this network is at 3.
It's what 3 now. It's 4.
It's weird. It's 4. Okay, thanks, Aula. That's it. Now we can do the last one. The last one is trickier, I think, because it needs an output with a timer. So let's say here that for the last one, we are going to have something like this. Perhaps it's not the best way, but we can do it like this. So whenever I go into state 4, I'm going to start feeding a timer, which is my timer on timer on 4. Okay, it's here. I don't know why my okay, so you know it's timer on 4, which has 8 seconds, and I'm going to activate some internal variable. Okay, so let's call it M10.0 and 8 seconds, something like this. Okay, just a name. It's an internal variable. That's why it's in internal Boolean variable. That's why it's in memory position M10.0. So okay, so this is an auxiliary branch. Let's call it an auxiliary branch, an auxiliary network. Sorry, auxiliary network. Okay, And now for the real network, I'm going to say, so when should I activate state S4? Again, the logic is the same. For the activation branch, I'm going to say that I need to be in the previous state, that's S3, and I need to transition based on a timer, which is the timer for S3, that's called T on 3. It takes 4 seconds, and that's when you activate state 4. For maintaining in state 4, it's the same as always, not really, because right now you do not have an next state. That's why we need this auxiliary method, because to do the final transition, we don't have next state. So it is the same. So the previous state is the current state, sorry, is S4, and here is while we do not have M10.0 and 8 seconds. Okay. Okay, so use this as an auxiliary just to be able to output. This is almost done. Well, not really. There are lots of other things that I need to do, but we have a lot already. Okay. Now, what should I do more? I should do state S0. You remember that I told you this is an exception, we'll do it later. So let's do it now. S0. When should we activate it? For S0, we always do it like this. We are S0, you think of it like a fallback state. What does it mean, a fallback state? It means that you go there whenever you are not in any of the other states. So I'm going to be in S0 is I am not in S1, not in S2, not in S3, and not in S4, because we have 4 states, well, 5 states. S0 is the first one. And furthermore, we can only be operating in states. Okay, so first, this is the end. Let's do it like this. Okay? So state S0 now is a fallback. It is activated whenever I'm not in any of the others. That's it. What else do we need to do? We need to make sure that these networks, it's not a single one, it's several, only function when we have the variable M2.3 activated. You remember this one? Only when this is true, we can be executing those networks. Okay. So to make sure that this is true, we are going to add here M2.3. And this is not only for state 0, it's also for the others. The auxiliary one doesn't really need it. Okay. So this is to make sure, remember this M2.3 is the auto. I can actually write here auto. This is to ensure that these networks only are executed.
Posso não ter a ver, mas isto basicamente não é para fazer um ciclo incrível, é só dar uma vez e.
Se tinha ficado, então, se calhar é melhor nem sequer fazer esta coisa. Não, mas já
Então, não está só aí, não sei aí.
não é para fazer um ciclo infinito, é para
Uma vez.
isso mesmo. Mas funciona, não é?
Sim.
Funciona. Porquê? Porque imagina que você faz isto tudo e volta a S0. Depois, para voltar a S1, tem que carregar mais 502.
Não é por causa do último. Eu fiz. Já está em modo automático aqui, basicamente no último, depois voltar ao início.
Mas
na última é quando fez de outra maneira para acabar, corre uma vez e pensar que não se.
okay. Okay, one more thing that I'm missing is we forgot. If you look at the PDF, it also says that the automatic mode can only be true if we have the condition BQ03. So we forgot here to add a condition PQ03, which is the water level in the well that must be above the minimum value. So how do we do this? There are several ways we can do it. We can say, we can put it here, and then we can put it here, and everywhere. I don't like this way, so my preferred way is to do like this. Okay, I can only operate in automatic mode if I have that special condition of having the water level. So I'm going to put it here. So I'm going to be in automatic mode if I have the selector saying I'm in automatic mode and I have enough water in the well. This is 0.3, not 0. If I put it here, I don't have to put it in the other methods, which makes it much easier. Okay?
That doesn't check. Imagine that I'm using the cycle of water and the water level, the well.
Falls below.
Yeah, possible. To always check this function before the.
That will depend what you do in your, so what you are going to do in your program is going to be something like this. You have your main, OB1. I always remember OB1 and OB1 main. This is the only function that is called automatically. Here you have to say, call FC1, then call FC, what is it? 12, something like this, okay? So if you do it like this, it will first call FC1, that means it will decide first whether or not it's in auto mode. Second, it will run FC12, that means it will run all these networks. If in the middle of this, your water falls below, it will still operate, but that's for 10 milliseconds. In the next loop, it will go here, and it will decide, oh, I cannot be in auto mode because I don't have enough water. So your response time is 10 milliseconds, but that's very short. Okay. What else? That means, don't forget, now in manual mode, what we must do is something like this. FC11, manual mode. So for manual mode, as I've told you before, what I want is to have my HMI show me some buttons where I can press and automatically activate. So what I can do there is nothing in manual mode. Okay, so what I don't think there is anything needed in manual mode, so I won't do it. And if we do need it, we will come back to this. Now we have the FC15. I will do it here. If I need, I will show output. Okay. So this is one part. I think it's FC16. Let me just make sure it is, because I'm not sure. So again, we do. So we can throw away the gallery. It's already away. We go here and here. And now we start again we split with the PDF, which is here. Okay. Now it is FC15 exit outputs. Okay, so FC15. For here, this is one of the places where you often make a mistake. And the reason for that is that you cannot put an output here. So what would happen if I do this? So let's say that I have M20.0. Right now, this is true. And M20.1, right now, this is false. Okay? Now, suppose that my networks, my program is like this. If I have M20.0, I'm going to activate Q0.2. And if I have M20.1, I'm going to activate Q02. What do you think will happen at the end of your loop? Will Q02 be on or off? Okay, off. Yeah, why do you say that, Miguel?
Well, because of the branching, if both conditions are verified, the program is in the scope of time, and the last one will turn it on.
Yeah, right. So the program is executed from top to bottom. So it will go to the network and say, oh, I forgot the M's here. M20.0 is on. Okay, so turn this one on. So now Q0.2 is true. Nice, let's continue. Next network. If M20.1 is on, turn on Q02. No, it's not on, so I should turn it off. Okay, so turn it off. Okay, so by the end of your control loop, so by the end of running your whole program, your Q02 is false. Let me tell you something else. So in another context, so you should open the door, if cold, okay? If it's cold, you should open the door. Well, perhaps makes more sense if it's warm. So if it's warm, you should open the door, okay? But you should also open the door if not raining. Okay? So if it's warm, you should open the door. If it's not raining, you should open the door. That's all. Okay? What happens if it's warm and raining? Should I open the door or not? Okay? No? Why not? Because it's warm, so I should open it. But it's also raining. So, but why are you giving priority to the raining part? Okay, so I ask you in another way. What happens if it's not raining and cold? Should I open the door? Yeah, this is like a paradox. You cannot have two logical functions. So, okay, in another context, y equals a b. Y equals c d. So if a and b are true, should I turn on y? I should. But what if a and b are false and c and d are true? Should I turn on y? Yeah, so this is like a contradiction. You cannot have two set of rules to define the output, the output state of a variable. Okay, in the PLC, when you do it like this, that's the first example. What the PLC will do is to execute the first set of rules and decide something, and then execute the second set of rules and decide something or something else, and overwrite the previous decision. In the other examples, Erica clearly is a warm person, so she wanted to open the door anyways, even though it's running, but this is not a straightforward decision, okay? So this is ambiguous, and we cannot have ambiguity in our PLCs. What's the implication of this? The implication of this is the following. I can even, okay, so I'm going to continue here for the FC. Is that we cannot have our outputs being turned on in different methods. And this is one of the most common mistakes that you do. So now I have my outputs, which are, where's the thing? Here, YV01. So that means in my FC15, I need to activate YV01. This is for watering sector 1. Okay. Now, when should I water sector 1? When I am in state S1. Makes sense, right? So when I am in state S1, I should water sector 1. That's it. Nothing more. Or is it? Because I also want to activate sector 1, the watering of sector 1, in another case, which is when I am in manual mode and I press some button. Okay. So let's call this button manual. Actually, this button comes from the HMI, so typically we call it HMI. Sector 1, S1, let's go. Sector 1. So if I press my button in the HMI, I should do it like this, okay? Now, what I typically do, just to make sure, okay, so the question that I had before is that this is the way to go. What the mistake that you often do is this. Okay? So this is the mistake. This is the idea of the, should I open the door or not, if it's warm and not raining. This is the mistake that you often do, and this is the contradiction for the program. This is like the first rule, and this is the second rule. And you are overwriting the first rule always with the second. So this doesn't make sense. You should do it like I told you before. Okay, like this. Now, the first branch is the automatic branch. And the bottom branch is the manual mode branch. I prefer just to make sure that this only operates. So, for example, suppose that you are running automatic mode, and then all of a sudden you go into your HMI console and you go into the manual mode page. That doesn't mean you are in manual mode, just means you are looking at the page. And you press HMI sector 1. This turns on. So then, for example, you in automatic mode, you would be in sector 2, watering sector 2, and then manually you would be overriding and you would be activating the watering of sector 1. So I don't like this mixture between. So automatic mode and manual mode should be exclusive, mutually exclusive. So they shouldn't be mixed. So to make sure that this doesn't happen, I'm going to make sure this only happens in manual mode, in automatic mode, sorry, and that this only happens in manual mode. Okay? And this is my output. I'm going to do the output for sector, for sector 2. Okay. This. So the output for sector 2 should be similar, quite similar. Should be here. When I am in state 2, I should activate sector 2 YV02. And when I'm in manual mode, there will be a button called HMI sector 2. That's it. Okay. Now, for sector 3, YV03, it's the same. I will let you do it. And for sector 4, YV04, I will also let you do it. It's more of the same. The only thing that it's not the same so this and this, I will let you do. The only thing that it's not the same is the lamp, okay? So that's the output HL00, this one. So for this particular output, HL00 signal auto, so that's for signaling the auto mode. I should do it when I am in automatic mode, so M2.3, auto. And now I should do it when I am in state 0. Remember by the way, when I created these outputs, this thing here, this auto mode branch, I could extract it directly from the graph set. I forgot to mention this. So For state S1, I should, so YV01, I should activate it when I am in state S1. This is what I did. Okay? For HL00, I should activate it in state S0 and S1 and S2. In any state, it should always be activated. So I can go here and I can do it like this. S1. And finally, here I will have S4, which is the last. Okay. You don't really need to put the states here because in auto mode, you can turn on the line immediately. I like to put the states there because it's more explicit. And sometimes we have some outputs which are only activated in some particular state. Like we give you the example of output. Let's write it in pink, for example. Let's call it out. This is just an example. Suppose that out is only to activate. In this case, I would have to say that out, the network would be out as, okay, 0 as 1, and finally the last one is S4. So you see, sometimes we want to activate in some special cases, and this is how we do it. Okay? I'm going to take the out away just not to confuse you. Okay, so that's it for, I think we have all the code developed. I don't think we need to do anything else, I think. Yeah, that's it. That's it, okay? So, unless I'm forgetting something, which I think I'm not, this is the whole code that you need to try to develop your program. Now, for the HMI pages, I've told you before, but let me explain better again. So, this is the root screen. So, hello. You should have a button for manual. This is not for entering manual mode and for entering automatic mode. That is again a common confusion. This is for entering the manual mode page and entering the automatic mode of screens. Then you have the manual mode. This manual mode should have some monitoring section or area that we call it monitoring. What do I want to see in my monitoring? I want to see the state of my outputs. So I want to see with a circle that turns red or gray if HL00 is on, if YV00 is on, and if YV04 is on or off. Okay? This is just monitoring, that means just observing the state of things. For the manual mode, I should have some control or direct control, let's call it direct control over the output. So I want to have a button for activating YV01, 00, another for YV01, and actually 4 buttons. You can even add a 5th button for turning on the lamp if you want. Now, for the automatic mode, okay, so I'm going to get more space here. copy, paste. So for the automatic mode, automatic mode display screen. So auto screen, let me call them screens to avoid the confusion I just told you about. Manual screen. We also have the monitoring. So typically what I do is I do the monitoring for manual and then I copy paste. So it's the same. Because this is not just not copying the elements, the graphical elements, it's also copying the functionalities. So remember for this one, you will have to say something like go to animation, appearance animation, when variable, which is the variable that activates AGL00. It's called AGL00, signal auto, something like this. So what I was saying, in the auto screen, what we want is to see the graph set. State S0, blah, 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 state S1, blah, 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 and so on and so forth. Okay? Don't forget to add everything that you have here. And then this graph set can be animated. I can show you an animation. I think I have it in my YouTube. Let me search. YouTube. Channel. Videos. No, the problem now is finding because this is always a problem finding stuff. How can I search? Here? Excuse me. Não, isto não é nos meus vídeos. Qual seta? Não, não tenho. Ai, certo, está aqui. Boa. Okay, so here's an example of an animated graph set, which you can try to do. It's a different problem. This is manual mode, okay? Manual mode. And now for the automatic mode, here. So here's the graph set. You can see that right now we are in state S0 because the S0 box is yellow. And we have several inputs and outputs. Those are these little squares which are green. That means they are on. For example, I just turned on ST01. Okay? And you just switch the color. Then when you start going through your graph set, so going from state S0 to some other state. Okay, so I just interrupted. Okay, so for example here, now I'm in state S1. This is with simulation, as you can see. Now I jump to state S2, and I am activating, I have these outputs and so on and so forth, okay? The monitoring part that I told you about is on the right-hand side. It's the right-hand side code. Okay, this is for inspiration. You can try to do it even better if you can. So now I'm just going to, I'm not sure what time is it? Let's put it on. So do you need something to get started more than everything I told you until now? Do you know how to start? Yeah? Okay, so do you need these slides or were you copying something? You were taking notes? Okay, so if you need them, I can give you the slides, no problem. But for now, just start, okay? So you should start a project and then start programming your code for doing this watering system. If you want, you can go out for eating something. It's 10 to 11, so we can meet back at 11 or something. Yes, the free patterns.